first of all, I'd like really to thank the organizing committee for the invitation at this event, which celebrates the birthday of Edmond Becquerel, really one of our heroes. So I will try to connect Edmond Becquerel with my work, which has been which dealt, with extremely high light, and like I call extreme light, and I will give you some really I will describe first how we can generate extreme light, and then I will discuss some of the applications. There is something which is very, very exciting about Becquerel is when you look at Becquerel, you find three names, three scientists. The first one is Antoine César Becquerel. The second is his son, Edmond Becquerel. And then you find, of course, the Henri Becquerel, which is the son of Edmond Becquerel. And so you have these three gentlemen, that covered about for 60 years. They covered, light and the birth of light, I would say, for 30 years, and light in all its aspects. Okay. So it's very exciting. What I like very much is the fact that I'm connected the most with Becquerel, Henri Becquerel, for the radioactivity. But when we talk about Becquerel, I think we talk about the Trinity, okay? Because the work of all of them have been really in one direction, and that is this continuum of work between Antoine César and Henri Becquerel, and of course going with Edmond Becquerel. So let me. That's right. That's my. I'm sorry. Okay, so one slide. Yeah, one slide I like a lot is this one, because you can see Henri Becquerel, Marie and Pierre Curie, and together they got the Nobel Prize, 1903, and on the radioactivity, and it's very much like and what you have to know is that Marie Curie was really a student of Henri Becquerel, and it was in that sense was very much like myself with my student Donna Strickland. Okay, so I'm really and Donna Strickland was the third woman, to get a Nobel Prize in physics, and of course Marie Curie was the first woman. So sorry. Okay, tell me what I'm supposed to do. I will try to do it. Okay, so you see, for me, I found this photograph very compelling with what we have done with Donna, and so I like it a lot. Of course, for me, to be the professor of Nobel laureates, is something that we can boast about. Okay, let me talk about my passion for extreme light. Okay, and so I'm going to why extremes, because you will see that the light that we are producing is a formidable, intensity and so on. I'm going to talk to you about how we can produce that and how we can use it. Now, we are the type of laser that we are going to use is a laser that emits extremely short bursts of light. Okay, typically in the billionth of a millionth of a second, 10 minus 15 seconds, a femtosecond. Okay, and because we can have these very short pulses, if we manage, to deliver this pulse with some relatively small amount of energy, then you can get, because the short pulse, the pulse is so short that you can get extremely high peak power. Okay, because of course power is energy divided by time. And for instance, we can now produce 100 joules, which is a small amount of energy. Okay, in 10 femtoseconds, and you have 10 petawatts. And 10 petawatt is 1/20th the solar power which is incident on the Earth. And it's about 3,000 times the grid power, the world grid power. So it's an enormous amount of power, but delivered in extremely short pulses, short time. So, but what can you do with that? I mean, you will see that there's tons of applications. First of all, if you focus this power, which is 1/20th the power of the incident light from the sun on Earth, if you really focus this power on diffraction limited spot, which means wavelength of light, then the power density is enormous. Okay, so the intensity is enormous, and this pressure, radiation pressure that you can get is enormous. It is in million times of the Eiffel Tower on the tip of your finger. Okay? So this is remarkable. This is just one aspect of this high peak power, but also you can produce, as I said, very high pressure, but you can produce also what we're going to see, phenomenal accelerations. Okay, and all that is going to be extremely useful for the application I'm going to describe. But having this ultra high peak power, move in optics, okay, in optics, moves the field of optics from the atomic physics to the subatomic physics field. Okay, you typically the atomic physics is typically in the electron volt regime, and so we can, if we go to the subatomic physics, you will be in megavolt, gigavolt, maybe tera electron volt regime. Okay, but now with this, that's a key idea I want to mention, is the fact that now we will be able to with light to go from the atomic to the subatomic realm. How we can produce these very high intensities is the following, and that's the reason why we got the Nobel Prize with Donna, is by the invention of a chirp pulse amplification technique of chirp pulse amplification. And it works this way. First, we start with extremely short pulses, which is provided by an oscillator at the nanojoule level, okay? And the short pulse is very short, so he has a lot of frequency, he has a broadband, of course. And so this short pulse first, what we are going to do, because we cannot really amplify directly this very short pulse, because immediately it will have very, very high intensity, and it will produce non-linear effect in a non-linear effect, or will damage the optical component of the laser. Okay, so with very, very short pulse, we were limited to very, very short, to relatively low intensity. Okay, but now what we are going to do is we are going to use this new technique to circumvent these problems, and it works this way. We take a very short pulse. The pulse, is going to be stretched, and we can stretch it with dispersive element, because the pulse, as I said, has a very, very, very broad band. Okay, so you are going to stretch it by 10,000, 100,000 times, or even a million times. And once you have stretched the pulse, the intensity has been lower, and you can amplify now. Intensity is reduced, so you can amplify it efficiently by using the amplifier without destroying the amplifier. And once you have harvested the energy out of the amplifier, then you do the converse of what you have done. You are going to compress now the pulse, and you can compress it back to the initial value. And so you can now produce extremely high peak power this way, and this is what we call extreme light. This is really the intensities that we can produce. We have been able to produce over the years, and starting in 1960 to today, you can see you have a very fast rise, and the relatively fast rise, and the fast rise stops at 10 to the 14 or so watt per square centimeter. This is really a regime where you are damaging everything. You are producing non-linear effect in whatever material you have. And then in 1985, we introduced this concept of chirp pulse amplification. And now we are going to immediately, we have been able now to go into very, very high intensity regimes. And when we increase with these high intensity regimes, we traverse, new domain, okay, new physics domain of laser matter interaction. And the first domain that we are really going to connect is the relativistic optics. I mean, first domain that we are going to encounter, I would say, is what I call relativistic optics. It is the fact that now with this, the field of your laser pulse is so high that the electrons are going to be driven, okay, at the speed near the speed of light. The electrons become relativistic, and that, of course, is going to lead to completely novel type of optics. Let me show you here. Here you see, if you see the, we know that the force which is applied on the electrons by the electromagnetic field is equal to Q, the charge of the electron, times E plus the electric field, plus V over C cross B, okay? Because the velocity of the electron in a general case, the velocity of the electron is so small compared to the speed of light, this V over C cross B will be able, is totally negligible, okay? This is in the common case. Now, with the laser, now the electrons, you see that this is a case number, case B. The electron will be able really to move now. With the force of the electron will be not only the electric field, but will also be acted by the magnetic field. And the electron, because of this V cross B, because the velocity goes, in y directions, and the field, I mean the electric field and the magnetic field, which are of course orthogonal to each other, you are going to have a V cross B, which is the product will go in parallel to the propagation directions. So now the electron, instead of going perpendicular to the propagation direction, will go, parallelly to the propagation directions. So it's a very, very radical change, okay? But you get once you are able really to drive, this electron to a relativistic regime. And so this means that I will be able now, really, to get the formidable field of the laser to accelerate the particles in the directions of the propagations. And so this is extremely important, going to lead to extremely important applications where we can now be able really to accelerate particles with a phenomenal field, and we'll be able to get very, very large accelerating field. So now the production of very high energy electrons is very simple. What we do is we focus the laser pulse into a plasma jet, okay, and we ionize the medium with, that means we separate the electrons and the ions, and you see you have the electrons which are going to be accelerated by this phenomenal field. And the type of what is remarkable is the type of accelerating field is enormous. It is in the GeV per centimeter scale, which is 1,000 times, easily what we can do with traditional way. What's that? Doesn't fit. No, shouldn't be. Oh, okay. Strange. So you see, as I said, we can now produce with a laser, with just a kind of tabletop system, we can produce GeV particles, okay, over few centimeters. Now, remember that conventional systems, for example, here I represent the slag, Stanford linear accelerator is typically 46 GeV, okay, 46 GeV, and that is 3.2 kilometers in length. And of course, with laser, it should be of the order of the GeV, should be of the order of 50 centimeters, of the order of few meters. Okay, so you see that is an enormous, of course, improvement. And the other thing is, of course, the electrons now, which clearly are accelerated from 0 to the speed of light in femtosecond time scale, is subjected to enormous accelerations in a 10 to the 23 G. Okay, so this is basically a means really to accelerate to really put these electrons in a is the analog. Basically, these accelerations, if you look at the equivalent principle of Einstein equivalent principle, these electrons are subjected to this acceleration, which corresponds to being on even correspond to be in the event horizon of a black hole of 10,000 sun. Okay, so this is really remarkable what we can produce now in the laboratory. Now, the other very, very important applications are really societal. And, for instance, among the societal applications, you have in medicine, the fact that we can produce, we can accelerate particles on a very, very short distances leads to extremely compact accelerators. Some accelerator that we can really, hopefully, one day, put it in every hospital to do things like proton therapy. Okay, proton therapy, this is really a technique of choice, for therapy of choice for to cure cancer. And protons, for instance, if you are very nice, because it's not like electrons or X-rays when you want to do therapy with electrons and X-rays. What you do is you are going to burn the tissue which sits before the tumor. Okay, but the proton is not. It's not bad. If you can adjust, the electrons or the proton energy, and so that the energy is going to be deposited, to the bright peak, and you can adjust. That is a distance that you can select, okay, by just adjusting the distance, the energy of the proton. So this is one of the applications which is extremely important. The other application which is also extremely important is the energy production. Okay, we know that now. Okay, it's we don't have a good way to produce, abundant energy in a very clean manner. Okay, and using extreme light, we could now we should be able to do that in a way. Okay, so I'm going to describe one application where we could use. First of all, why do we try to go nuclear if we can do it in a very clean way? It's because nuclear energy is extremely, could be extremely abundant. Okay, and I would say that, and also very efficient, because, for instance, to produce 1 gigawatt power, over a year, it takes, with coal, it takes 100 trains of coal, 100 trains of 100 wagons of coal. Okay, if you do that now with uranium, then you need only 300 tons of uranium. And if you are using thorium, for instance, well, you can really use only 1 ton of thorium. So there's a huge incentive to go nuclear if you can really solve the problems of nuclear waste. Okay? And nuclear waste, which is produced when you are producing this, when you're producing this energy, the fish, as you are doing, you send these neutrons that you are produced with the laser, then some of the neutrons can be captured by the nucleus and make change the nucleus, and you make what we call minor actinides, which are very dangerous species. Now we had the chance with Donna to meet the Pope about this recently, because the Pope, of course, is extremely concerned about producing clean energy, okay, for humans, for Homo sapiens. And so that was, we had a very, and we were discussing our plan how we could really use our extreme light, to produce clean energy. Now, another very important application, and after that I'm going to stop here, okay, is really producing this, trying to clean up the space, okay. You know that the space has been cluttered with enormous amount of debris after the first launch, the first Sputnik launch, well, in 1957, okay? And we are in a situation where we have millions of debris, circling around the globe. And so some are very big, but not many. I mean, you have maybe 1,000 big debris of the size of cubic meter size, or that kind of thing. But you have millions of debris of a centimeter size, and you know that these debris move at about 10 times the speed of the velocity of the fastest of bullet. Okay, so these can really be very, very damaging. And right now there is about we send something like 4 Eiffel Tower, in the sky, in space. Okay, and about now you have a half Eiffel Tower, which is under the form of debris. So now I'm going to show you a clip, and I will stop after this clip, where showing that what we can do in order to clean up the space, okay, with lasers and with extreme light laser. So first I will start with an event which occurred in about 20 years ago, when the Chinese, trying to demonstrate that they were able really to shoot a satellite, in space, one of their own satellite, with a rocket. Okay? And in doing that, they did that successfully. But what was not so good is that they produced a huge, enormous amount of debris, okay, millions of debris, and something that we likely to avoid. So the clip is showing you this. Then it shows how we are going to tackle, the cleaning. Okay, we are not going to blow the debris with the laser, but what we are going to do is we are going to nudge the laser by sending the laser and I will say with the force we can ablate a part of the debris, and this ablation is going to really act as a rocket effect and will deorbit the debris, and the debris will fall into the atmosphere and be burned into the atmosphere. So this is about the clip you are going to see, and you are going to see that we are using also a new type of lasers, but which is based on fibers, and here you go. Okay. Je pense qu'on n'a pas le son. Ah, on n'a pas le son. Okay. Well, I guess we have a problem. We cannot get the sound. So I'm going to end at this point. Thank you very much. And if you have any questions, please do not hesitate. Thank you very much.
Thank you very much, Gérard Mourou, for this impressive travel in laser physics and applications, and also opening all the debates on the use of light. And I think it's extremely interesting to have your vision. And I may have one question. I think that what could be when for the application, how did it came to you to use a laser for the application in ophthalmology?
Yeah, that's one big application that we can talk about it, because I thought it was kind of connected with this conference, was of course the application in ophthalmology, which is a fantastic application, because now millions of people are getting these procedures. No, it happened because, like many times in science, it happened because of just a stupid accident where one of my students was tweaking the laser, and by doing so, he got the laser in his eyes. And he was a Chinese student, so he came to my office. He was completely destroyed, because he knew that in the States, when you have an eye injury, basically you have to close the lab, okay? And he knew that he will have been responsible for that. So he said, I'm really sorry. I got the laser in my eyes. Say, don't worry, Dita. Let's go first to the hospital, and we will see later what happened. And in the hospital, the intern, will look at my patient, my student, say, wow, yes, you got the laser in your eyes, but it's amazing. And the students say, why is that amazing? Because it's a perfect damage. The damage is perfect, very clean, okay? Very small and very clean, okay? And this intern understood immediately the application for the ophthalmology. I have to say that, of course, before ophthalmologists were using lasers, but they were using lasers with very long pulses. So you are making really a lot of damage, you know, when you are using the lasers. It was not clean. But with the femtosecond laser, it is the perfect scalpel. Very, very clean. The edges are it's beauty. And then when we met, of course, the president was aware of that, of this accident. So we had a big meetings and so on, and the University of Michigan, where I was at that time, were going to discuss, okay, what we are going to do the lab. Are we going to close the lab or so on? So I made a presentation and so on. And after this presentation, I thought my lab was going to be closed. Okay. After the discussions, they reconvened, and they told me, well, the president of the staff told me, Gérard, I say, wow, my goodness, my lab is going to be closed and so on. He said, well, then we decided to give you $500,000 dollars to push your activity in these directions. And but I think a lot of times, you know, people say, okay, what's the difference between France research and research in the United States? And I always have that in the back of my mind, but I don't think that will have happened. And then it was the beginning. It took about several years, of course, you know, to get the FDA approved, and then we had it was enormous amount of. It was a great success. Great success.
Thank you.
Okay.
Thank you very much
also
for this history, personal history. So, Alexandre, so we have we have a delay in our program, but it's fascinating the discussions with the presentation. So I hope you are still in line, and I pass the floor to.
Okay.
Thank you very much. Merci beaucoup, Professeur Mourou.
Merci beaucoup, Gérard, pour votre présentation.